Hey guys, this is the last lesson in Chapter 9, Differential Equations. This is our third and final method on how to integrate these differential equations and come up with either general solutions or particular solutions if there's an initial condition. It's called the integrating factor. And the integrating factor always comes in this form. You might see it look like this: y times p of x, dy dx plus y times p of x. That could be minus y times p of x equals q of x. I'm going to show you all the mechanics to that. You might also see y prime plus, say something like p of x times y equals q of x, and any sort of possible combination of that setup, okay? But that is the form that we want to get this differential equation into in order to use this method. Okay, a little bit of integration help. This is really good practice. So I'm going to just do this or give you some tips on the side, and I'll come back and explain it. Okay, so for the first one, what I would do is I would just bring this e to the 3x to the numerator and integrate from there. It should be pretty easy from there. You'd probably just bring out, your 1/3 or negative 1/3 and have your integral set up real nice there. Think natural log here, okay? If your degree in the denominator is 1, think natural log, unless it's like number 3, where you've got yourself a u substitution situation here, okay? And then here, there's no u substitution. What should I do? Well, that's going to be an arctangent, right? Recall that 1 over a squared plus x squared is going to be arctangent. So just some tips. We can go over those in class if you'd like. Hey, some more here of a very similar form. Okay. I would, like I said, probably same thing on number 1 here as I had before. I would bring that to the numerator and integrate. Here's a natural log. Be careful with this negative. Here's a u sub. Be careful again with the negative. And then here I would bring to the numerator, making this 5 minus x squared to the negative 1/2, and go from there. All right, guys, let's jump into the integrated factor. Of course, I have a different problem. This is a homogeneous method here. For the purposes of time, I'm going to do part of this off camera. Alright, so let me quick walk you through what I've done here. I divided both sides by xy and simplified this side to 2 over u plus u, right? X over y is the same as 1 over u. This will be the same as u. These two u's will cancel. So I'll get du dx, recall our substitution here, right, for dy dx. These two u's cancel, and then I divide both sides by x. And so from there, what I would do is I would just get u over 2 du is equal to 1 over x dx, and then we integrate. So I'll integrate that, fun. That'd be u squared over 4 is equal to natural log of x plus c. In comes our initial condition, which is e squared e. Okay, so u squared is really y squared over x squared. Alright, and that's going to equal natural log of x plus c. So I think it was e squared e, wasn't it? E squared e. Okay, so that means x is e squared when y is e. Okay, so when y is e. Therefore, I get e squared over 4e to the 4th. So that'd be 1 over 4e squared is equal to, well, the natural log of e squared is 2. So it looks like c will equal 1 over 4e squared minus 2. Okay, so I can take it back to this step here. So I get y squared over 4x squared is equal to the natural log of x plus this thing, right? Plus 1 over 4e squared minus 2. Maybe I'll make that a little bit more compact. Let's make that 1 minus 8e squared over 4e squared. Okay, all I did was multiply that second piece, that 2, by 4e squared, top and bottom. So that's 1 minus 8e squared, da-da-da. Okay, so if I wanted to solve then for y squared, I would just multiply both sides by 4x squared. So I'd get y squared equals, and I'd probably just write it like this, 4x squared times what I had already had there on the right side. Alright, that would be a particular solution to that differential equation. I'm only like that. I'm not going to take the square root of both sides, but I could. If I did, right, I'd get this plus or minus, and actually I would only get the plus portion of that because in this case our y value came out to be positive, right? So there you go. There's a little review on the homogeneous method. Alright, so let's get into this idea of the integrated factor. This video, I'm not going to prove the integrated factor. I'm going to do that in a separate video that you can watch on your own. But what the integrated factor comes out to give us, and it's pretty wild, is it allows us to solve for this y using this idea of p of x and q of x, and then this other thing I'm going to come up with, which is I of x. Okay, and I of x is called the integrated factor, and I of x is equal to e to the integral of p of x dx. Okay, don't go into like, what? Like, you're gonna freak out the first couple times you do this, and it's an amazing thing. But p of x, all it's used for, this guy right here, is just to find us I of x, because really this right here and this right here just become I of x, and then we don't use p of x at all in our actual steps at the end. Okay, so let's look at an example. Right, this is in the form, I'm going to write it like this just to save some space. F prime plus p of x times y is equal to q of x. So you can see that p of x equals 2 and q of x equals x. Okay, so let's get our integrated factor I of x, which is equal to e to the integral of p of x dx. Alright, so our integrated factor in this case is equal to e to the 2x. Okay, now we won't put a plus c on here, and I think I cover that. I cover that in the proof of the integrated factor. But now I can use this form that I have over here, you guys. This thing. So d dx, the derivative of y times I of x, is equal to q of x times I of x. Okay, that's q of x. Oops, I forgot e to the power of that times e to the power of 2x. Okay, and now, believe it or not, this is a separable differential equation. And you'll see it in just a moment here. I'm going to integrate both sides. Unfortunately, that's going to require some integration by parts on the right side. But if I integrate a derivative, it just comes out to be said thing, right? So I get this. On the right side, I'm going to have to do some integration by parts. Let's see what that comes out to be here. So I think u will equal x, dv will equal e to the 2x dx. Can't forget my dx on the end there. So du will equal dx, and v will equal 1/2 e to the 2x. Okay, so what this will equal, remember, integration by parts will be uv minus integral v du. So uv will be x e to the 2x over 2 minus the integral of v du. Okay, so v du will be, I'm going to pull the 1/2 out, integral of e to the 2x dx. Alright, so it looks like I'm going to have to do one more round of integration here, but it won't require a whole lot, just a quick calculation here mentally. So let me just check back here for a moment. Okay, sorry there, I was questioning whether or not I did this right, but I did. Okay, so I'm going to leave the left side alone, y times e to the 2x, and on the right side I'm just going to integrate what I have there, so I'd have x e to the 2x over 2, and it looks like minus 1/4 e to the 2x. Okay, so I'm going to divide both sides. In this case, to get y, I'm going to divide everything by e to the 2x. Divide this by e to the 2x as well, and you're going to see something pretty extraordinary come out of this. It looks like e to the 2x cancels with both of those items, and I get x over 2 minus 1/4. So the differential equation in this case comes out to be a linear function. It's pretty amazing how that all works out, but yeah, that's integrated factor. Let's try another example. Okay, so dy dx. Alright, I want to get in my form that I know, so I'm going to bring this, I got dy dx here, I'm going to bring plus y over here and e to the negative x over there. So p of x, in this case, is the coefficient of y, which is 1. So p of x is 1, and q of x is e to the negative x. So let's do some work. I of x will equal e to the integral of p of x dx. That's 1 dx. So it looks like I of x is going to equal e to the x. So d dx is equal to y times I of x, or d dx of y times e to the x is equal to p of x times q of x. Or excuse me, I of x times q of x. Now if I multiply e to the x and e to the negative, so e to the x times e to the negative x, what do I get? I get 1. I get 1. So d dx of y times e to the x is equal to 1. Alright, let's integrate. I integrate both sides with respect to x. The left side just becomes what it is on the inside there, and the right side becomes x. Let's see here. Is this general? No, it's got an initial condition. I gotta add a plus c here. So here we go. I would, in this case, divide both sides by e to the x, but I'm not going to do that yet. I'm going to plug in my point 0, 1. So if I plug in a 0, I get a 1. Plug in a 0, I get a 1. That means that c, in this case, will equal 1. Therefore, y times e to the x is equal to x plus 1. And so what I get here for my particular solution looks like x plus 1 over e to the x. And there's our function. Alright, let's try one more here. Initial condition 1, 4. Looks like p of x is 5. Q of x is equal to 6x cubed. Oops, problem here. We got to divide everything by x. Okay, so p of x now, this will cancel. P of x is 5 over x. Q of x is equal to 6x squared. There we go. So if I want I of x, I take e to the integral of 5 over x dx. So it looks like I of x is equal to 5 times the natural log of x. Alright, so d dx of y times I of x is equal to I of x times q of x. 6x squared, and I'm going to make this about 30. 6 and 5 would make I times q, yeah, that'd be 30x squared natural log of x. Okay, so I think that I'm ready to roll here. I'm going to integrate both sides as we've done up to this point. The right side looks like it might become a little ugly. Okay, the left side is what it is. I'm going to say integration by parts here. And u is going to equal natural log of x. dv will equal 30x squared dx. So du will equal 1 over x dx. Oops, not dx, just 1 over x. Actually, no, yeah, that's right. 1 over x dx. And v will equal 10x cubed. Alright, so this would be uv, which is 10x cubed natural log of x minus the integral of v du. Now if I multiply these two together, I'm going to get 10x squared. Right, I'll get 10x squared because the 1 over x and the x cubed will simplify. And all I got to do is integrate that. So let's do so. Alright, so I'm going to move down here. I'll get y times, actually let's go 5y times natural log of x is equal to 10x cubed natural log of x minus, what would that be, 10 thirds x cubed plus c. Okay, let me check over my work real quick. Looks good to me. And I got an initial condition of 1, 4. So y is 4 when x is 1. Well, I get a 4 here. If x is 1, I got issues and problems there. That's going to be 0. This will be 0. That'll be 1. So the left side will be 0. Over here I'll get 0 minus 10 thirds plus c. So it looks like c is 10 thirds. So I'm going to work my way back here to save some space. And I'm going to put a 10 thirds on the end here for c. 10 thirds. Okay. So let's go ahead and get this all figured out. Okay, so we've got, this would be 5. Oops. I'm going to divide everything by 5y, or 5 natural log of x. That's an ugly one. The 5 will cancel everything out here. All these 10s will become 2's. So I'll get 2x cubed natural log of x. This is an ugly one. 2 thirds x cubed minus, plus 2 thirds. And all of that divided by the natural log of x. Whew, that was an ugly one. Alright, but that is the integrated factor. That is the function that gives us this as our derivative way up here. Alright, let's walk through maybe 1 or 2 homework problems and we'll call it a day. Alright, I like this one. Let's go ahead and do this one. Okay, this is actually a really good one. Alright, so I'm going to divide everything by tan x. Okay, but instead of dividing everything by tan x, I'm going to multiply everything by cotan x, and cotan x is the same as cosine of x over sine x. Right, so if I multiplied tan x by that, that would disappear, so I'd get dy dx. If I multiplied y by that, right, I would just get cosine x over sine x times y. And if I multiply sine x by that, I would just get cosine x. Okay, so I see I got my p of x here, I got my q of x here, and now we're rolling, right? And I've got this initial condition of pi comma 0. So let's get this thing set up. I of x will be the integral, e to the integral of p of x dx, cosine of x over sine x. This is going to require you to do a u substitution. So if you set u equal to sine x, du equals cosine x dx, and therefore you would get 1 over u. This would be e to the 1 over u, right? Integral of 1 over u du, which means that you'd get e to the natural log of sine x. Okay, and this is one of my favorite problems for this reason. This uses just about every skill you have in the book. E to the natural log of something is just that something. So I of x, in this case, is going to be sine x. Okay, and we know that q of x was cosine x. And we know our initial condition was pi comma 0, so now we can roll with this d dx of y times ix is equal to qx times ix cosine x sine x. Okay, and let's integrate this thing. Integrate both sides with respect to x. I get y times sine x is equal to this over here. I would do a u sub for. So if u equals, let's say, sine x, then du equals cosine x dx. So then this integral becomes the integral of u du, which is equal to u squared over 2 plus c, right? So I get sine squared x over 2 plus some value c. All right, let's use our initial condition here to find out what c will equal. And let's see, so when x is pi, y is 0. All right, so I get 0 times sine of pi is equal to sine squared of pi over 2 plus c. Well, sine of pi is 0, so we get 0 equals 0 plus c. So c equals 0, so that's kind of nice. Take that all out of there. So all we got to do in this case is just simplify for y. We're almost there, real close. For whatever reason, I can't erase that stuff. That's going to bother you and me. So let's divide both sides by sine x. Recall that c is 0, so it doesn't matter. So it looks like y equals sine of x over 2. Awesome. Okay, let's just identify real quick p of x, q of x in this case. It looks like p of x equals 2, and q of x, I feel like we've done this one, but maybe not. Something similar maybe. There you go. So I see an integration by parts coming on there. Or nah, maybe not. No, yeah, it's an integration by parts. Okay, p of x equals 1 over x. Q of x. Ooh, that one's nasty, but that'll just be a q of x will be natural log of x over x squared. Yeah, so you're gonna get something interesting there, but that'll be a fun one. Okay, it looks like if I rewrote in this form, like P of x. This guy just must be digging out integrated factor and just figuring out P of x and Q of x. Just pulling them out of the snow. P of x would be 1, Q of x would be, as it looks like, e to the negative x. This one's going to be funky. So it looks like, boy, what would I do? Okay, yeah, I do this. dy dx looks like minus xy over x squared plus 1. When you integrate P of x in this case will be x over x squared plus 1. That's going to be a u sub. And then it looks like Q of x, not typical, but it equals 0. Yeah, it would equal 0. That's an interesting one. That'll be fun. Here, again, this is pretty much straightforward. There's your P of x, 2 over x. There's your Q of x. Boom. That's going to be a fun one, too. And the last one. Yep, okay, here you go. Just a little bit different notation with y prime. I would bring this over to this side, so I'd make it minus and this an equal. And when you divide by cosine of x, you get y prime minus, looks like tan xy is equal to, this is interesting, but this is 2 sine x cosine x over cosine x. Right, sine 2x is 2 sine x cosine x, so the cosine x's will cancel. And so your P of x is negative tan x, and your Q of x is 2 sine x. That's going to be a fun one. All right, that'll be it for today. Integrated factor, we'll get plenty of practice in class. Peace.